Here is our Pre-Calculus 2-1 Day 2 assignment. I did already try to record this and got interrupted about 300 times, not kidding. And so we're just gonna try it again. Okay. So, in number 45 here, again, we're trying to describe the strength and direction of this linear correlation. So as you can see a trend kind of going this way. So remember that strength just means how close is it to a linear line that you could draw. And so in this case, number 45, we would say it's strong. And then along that lines, we'll also see that they're asking for direction. And so notice that it's going up from left to right. And so that's where we would add that it's positive. Again, meaning that it's a positive slope if you were making that line as well. Alright, then in 46, you can see that it's a negative, okay? You can also see that it's pretty strong as well. It's pretty much around there. So you can either say it's strong or weak. I'm going to say it's strong. And I'm going to say that it's negative, of course, because the slope of that line is negative. Then we have number 47, and this is the one where I would start to say that it's more of a weak relationship, but if you want to go with strong, okay. And then we're going to go with positive, because the slope of that line is positive. And then the last one, depending on how precise you want to get in number 48, we're going to say that it's weak, and that there's pretty much zero correlation or strength. So potentially you could kind of follow how this goes up, or you could kind of say this kind of goes down, but either way the data is pretty evenly spread out, which means it's weak. Alright, so the next piece is number 54. In number 54 we're talking about all the rectangles whose perimeter are 100 feet, and we need to find the dimensions of the maximum area. So you got to watch out because it's saying perimeters and area. And so we're actually going to have two formulas. One of them is for perimeter, which is going to be twice the length and twice the width. And then the other one is going to be area, and that's going to be length times width. The other piece that I didn't put in here is that the perimeter, they actually said, is 100, so we can plug that in. And so now we have this system. And so in order to get the area that we're trying to find maximum, I'm going to rewrite this top equation in order to plug it into the next equation. So if I take that top equation and set it equal to length, for instance, if I subtract a 2w, I'm going to get 100 minus 2w. And then if I divide everything by a 2, I now have a length that's 50 from 100 divided by 2, and then minus w. So that length can actually go back in to this other area equation, and so we only have one variable left, and so our area equation is 50 minus w times w, because that used to be the length. Now we're trying to maximize this area equation, so all we want to do is find the maximum. And so the best way to do that, I guess, would be to graph. It's probably the easiest to find the maximum. But you could also use the fact that this is a quadratic and use the quadratic equation to find... oh no, those would be zeros. You can use that idea of the x value of the maximum is negative b over 2a. We did that in our notes the other day. I'm liking the graphing it at this point, so I'm going to go ahead and graph. And of course I'm not going to graph it the way it is. I'm going to graph it as 50 minus x times x. So if I graph that, I'm going to find its maximum. And of course, once you type that into your y equals, if you graph, you're ending up with a very tiny amount of lines or visual. So if you go through and kind of extend your graph a little bit, let's see. Okay, so I ended up extending the x's out to 50. and then the y's doesn't really matter, but I went up to 50. And so the idea is that you actually have this graph, the only part of which you can see is this. And so there's this other piece in here that we're going to find the maximum of. So basically when you're doing this, you're going to want to find the maximum by picking a point that is close to 0 to be your left bound, and then close to 50-ish to be your right bound, and then it's going to be somewhere in between. You can actually type these numbers in, so if you go to second calc and then to the maximum, instead of scrolling left and right, you can go ahead and just press enter as your left bound, and then your right bound you can just type 50, and then for your guess, I don't know, 25, doesn't really matter as long as it's between 0 and 50, and then it turns out it actually is 25. So our x value is going to be 25, as in our x is actually our width. And then the maximum area at that point is going to be the y value, which is 625. Alright. The next one is a little bit more tricky, only because of this piece right here in thousands. So whenever they're talking about 100,000 units, for instance, they're actually just talking about 100. Or when they're talking about 1,000,000, it's just 1,000. You always just kind of take off 3 zeros there. So reading through this problem in number 55, the per unit price, P in dollars, of a popular toy when X units in thousands are produced is modeled by the function. And so our price here is given as 12 minus 0.025x. The revenue is actually the price times the amount of product that you make, right? So in that case, x times P, or x times our price equation. And so the first thing they want you to do is state the dimension of a viewing window that shows a graph of the revenue model for producing 0 to 100 units. So if we think of what they're asking for what is your window going to be in order to be able to display between 0 and 100 units. So basically they just want to know how high does it need to go. Well, if you take the time and plug in an x of 0, you're going to get a y of 0. So that just means that it starts down here. And then if you go ahead and plug in an x of 100, right, because that's what they want there, you end up with a y of, we're plugging it into here, by the way, you end up with a y of 950. So, just double checking my notes, yeah, okay. So in that case, that means that up here is going to be about 950, so how high do I want this screen to go? Technically to 950, but you can always just do 1,000. Usually you want your window to be a little bigger than what you actually want to view. Alright. So, so the answer to that one is going to be from 0 to 100 for your x values. And for your y values, you want it to be between 0 and 1,000. Alright, for part B, you want to know how many units should be produced if the total revenue is to be 1,000,000. And remember that 1,000,000 is actually going to be 1,000, as per what I was saying at the beginning. So we're just trying to find out when will this revenue equation equal 1,000. So there's a few ways that we can do this. One of them is literally setting it equal to 1,000, as I've shown here. Or you can go ahead and find where the graph meets 1,000 if you maybe graph this equation on a larger scale than what we did in part A, because we're going to be going further. And then drawing a line at 1,000, so just y equals 1,000, and see where they meet. If you don't want to do that, on a different slide, I'm going to do number 55B. And so again, I'm trying to find out when does 1,000 equal the equation that we just got, which was x and something, can't remember. 12 minus 0.025x. And so in order to solve this, we're going to want to distribute. And then in order to get where we want to go, we need a 0 equal, so we'll subtract this 1,000. And then you can hopefully see that it becomes a quadratic of negative 0.025 x squared plus 12x minus 1,000. Then we go through and we're trying to use an a value, in this case, of negative 0.025, a b value of 12, and a c value of 1,000 into your quadratic equation. So x equals negative b plus or minus square root of b squared minus 4ac over 2a. There it is. And so we just go ahead and plug in each of those pieces. So negative b is 12. Then we add and subtract 12 again. Square that and then subtract 4 times a, which is negative 0.025. And then c, which is negative 1,000. And then divide that all by 2 times your a value again. Alright, so our x's are going to equal both of those. And it turns out you actually get 2 values of x. So x becomes negative 12 plus or minus the square root of 44 if you evaluate inside that discriminant there. And so we're going to end up with negative 12 plus square root of 44 over negative 0.05. And we're also going to come up with negative 12 minus the square root of 44 over negative 0.025. Oh, sorry, just 0.5. Those values officially work out to be, for this first one here, 107.335. And then for this second one, we get 372.665. Now, of course, these are answers that are actually in the thousands, so our answers are going to be 107,335 or 372,665. And that's units that should be produced in order to make $1 million. Again, the reason there are 2 answers is because if you graph, you will see that it's going to go up. Whoops. It's going to go up and then back down, and it's going to hit that 1,000 mark twice. And so those 2 pieces are where we're meeting the 107,000 and 372,000. All right. Moving on to our next problem. Looks like it's this free fall motion. As a promotion for the Houston Astros downtown ballpark, a competition is held to see who can throw a baseball the highest from the front row of the upper deck of seats. Okay. Those upper deck of seats are 83 feet above the field. And so this winner is going to throw the ball with an initial velocity of 92 feet per second up into the air, and then it's going to end up landing on the field. So hopefully you can see how that looks like a parabola. Okay. Yay, quadratics. So the next piece is to find the maximum height of the baseball. So we want this guy right here. And so how do we find the maximum height? Well, first we need an equation. So the equation is going to come from the fact that height in terms of time is negative 16t squared minus the initial velocity and then plus the height. I think there's a minus in there. Apparently not, it's plus. Okay. So now we get to fill in our pieces. Looks like 83 feet is going to actually be our initial height, or h with a little 0. And then our 92 feet per second is going to be the velocity with a little zero of initial. And so our height equation becomes negative 16t squared plus 92t plus the initial height of 83 feet. Alright, so if we want the maximum height of the baseball, there's a few ways of doing that. Clearly we could graph and find the height, or we could actually just use the formula that we had in the previous problem, which was, in our previous notes, which was that the vertex, the x value of the vertex comes from negative b over 2a. So if this is our b value and this is our a value, our vertex is going to be negative 92 over 2a. So 2 times negative 16. Of course, that's only the x value, and so in order to find that height, we'd have to plug in the x to get the y. But either way, that means that our x, or the time, is going to be at 2.875 seconds. And so then we take that t and plug it back into each of these pieces in order to find the height. So our height is going to be negative 16, 2.875 squared, plus 92 times 2.875 plus 83. And when you calculate that, that means that your height is actually at 215.25 feet. So that's part A. Oh, sorry, part... Yeah, A. Then we need to know how much time is the ball in the air. So I'm going to do that on a different sheet. And this problem is number 61. So again, how much time is the ball in the air? So taking that formula and finding out when that height equals 0. Because once the height is 0, we're going to end up having it hit the ground. And so we solve this, and you can solve it with the quadratic formula, or you can graph and find where it intersects at that time. But I'm going to use the quadratic formula. So this is an a of negative 16, a b of 92, and a c of 83. So to find that time, we need negative b plus or minus the square root b squared minus 4ac all over 2a. Alright. So if we plug that in, we have a negative 92 that we're going to add and subtract to 92 squared minus 4 times a, which is negative 16, times c, which is 83. And that's all over 2 times our a of negative 16. If we work through and solve, we're actually going to be looking at the square root of 13,776, and all of that over negative 32. But of course that splits up into the two answers of what happens when you do the plus and what happens when you do the minus. So when you work in the plus, we're going to get let's see, negative 0.7929 seconds, which is weird. And then when you plug in, because time doesn't go backwards, then we plug in for subtraction 6.5429 seconds. And so if we think back to the image, that's saying that if the ball had been actually thrown from the ground, then reached up to the stands that were 83 feet above, which is technically where it starts, and then continued on, we actually have 0.729 seconds in this first bit, and then 6.5429 in this second bit. So basically it's going to take from 83 feet above the ground for this ball to go up and land again, is going to take 6.5429 seconds. Alright, so continuing on, part C. We didn't go over a problem like this in the notes, but part C is asking you, okay, now that you know how to do this, let's go ahead and do it backwards. So we're going to determine the vertical velocity when it hits the ground. So taking a look at what our equation is actually saying, this is part C. Your equation is saying if your height is this, and you're given negative 16t squared plus the velocity and t plus the height, initial height. They actually want you to plug in this t that we just got. Oops, I'm on the wrong page. And so the t we just got of 6.5429 is going to go in here. And then the height, because we are looking for the velocity when it hits the ground, we're not going to put in this initial velocity because we don't actually want that. We want the ending velocity. So this is going to be what we try to find. You know, this all seems lovely, but as I'm looking at this, the only way to get the answer of 117 is to use a formula that we didn't actually get. So turns out that C we can skip. Technically, if you want to continue on with it, to find your velocity, which we didn't talk about, you would take your initial velocity minus the pull of gravity, and then times your time. So we would have put 6.5429 in for time, and then we put our velocity initial of, how fast did we say? Threw it up there, 92 in for the initial velocity. So if you wanted to go ahead and do that, you can go ahead and skip that one. Anyway, so moving on to the next piece. The baseball throwing machine, woohoo. The Sandusky Little League uses a baseball throwing machine to help train 10-year-old players to catch high pop-ups. It throws the baseball straight up with an initial velocity of 48 feet per second from a height of 3.5 feet. So we need to find an equation that models the height of the ball t seconds after it's thrown. So again, that's going to be our formula from before, where we have the height is equal to negative 16t squared plus the initial velocity times t plus the initial height. So officially our throwing machine equation is going to be negative 16t squared plus the velocity of 48t and then the height of 3.5 for how high the machine is standing. Then in part B, they want to know what is the maximum height the baseball will reach and how many seconds will it take to reach that height. And so again, that's just looking for the vertex. And so two ways we can do that. You can find the maximum using your calculator, or you can use the fact that x equals negative b over 2a, where our b is 48, and our a is negative 16. And then you can plug in your x. So that's the way I will do it. So again, our height equation is, oh sorry, we don't need that. The equation we're plugging in is for the x value, or in this case the time, and it's negative b over 2a, or negative, what was our b value? Negative 48 over 2 times negative 16. Okay, so negative 48 over 2 times negative 16 becomes 1.5, and so that's 1.5 seconds, which answers part of that question. The other part asks you how tall is that. So if our height, or our y value, is taking that equation and plugging in the seconds, oh, the initial height was 3.5, yeah. For the t, we just need to solve where 1.5 is being plugged in for the t. And that will give us our height. And so evaluating that, we're going to get 39.5 feet. And so again, half of the answer is how tall, and half of the answer is how long it will take to get there. Alright, then in number 63, we've got some fireworks planning at the Bakersfield 4th of July celebration. Fireworks are shot by remote control, excellent, into the air from a pit that is 10 feet below the Earth's surface. Okay. Find an equation that models the height of an aerial bomb t seconds after it is shot upwards with an initial velocity of 80 feet per second. So of course we're going back to our equation of height and velocity. So filling in what they're giving us, the height initially is going to be negative 10 for it being 10 feet below the Earth's surface, and then 80 feet per second is going to be our velocity. So the equation that they want us to graph is negative 16t squared plus 80t minus 10. So the graph that you're looking at least in order to get the whole picture here, is going to be down to negative 10, which it normally is, and then over to negative 10 in your x's and over to positive 10, but you are going to want to go up to about 100 so that you can actually get the entire maximum image. So if we graph it, it's going to look like that, more or less. Alright, so they're asking what is the maximum height above the ground, and so of course we get to do our maximum either calculating since we graphed it, or you can do it algebraically, and since it literally is just sitting here, I'm going to go ahead and second trace and go to a maximum. So I'll go left bound at 0-ish, right? Right bound at maybe 5. And then guess of about 2. And so when we do that, we're going to end up with an x of 2.49999, so 2.5, and a y of 90. So that means 2.5 seconds after that launch, we're going to be 90 feet in the air. That's your highest height. Alright, the next two problems I'm going to have to do on another video, but that is it so far.